All right, so today here on our notes or our explore task, you're going to be asked to do 8.2 and 8.4 and then upload those as your notes. So if we take a look here at 8.2, it says a tessellated trapezoid. You don't really have to know too much about what tessellated means, but essentially we're looking at this trapezoid and how we can solve it. So here's a pattern showing a trapezoid being successfully decomposed into four similar trapezoids at each step. So basically, we're taking, say, step 0, you've got one trapezoid. You look at step 1 after we've decomposed it into essentially breaking it up into more trapezoids for every single step. So you can see, all right, well, that goes from, let me grab a pin here. This is one trapezoid. Here we're going to have 4 trapezoids. And then if you look here, each trapezoid inside is now broken up into 4 more. So each of the 4 trapezoids now have another 4 or 4 times 4, which maybe you can see there is 16 trapezoids. All right. So if n is the step number, right, which step are we on? Step 1, step 2, step blah, blah, blah. How many of the smallest trapezoids are there when n is 4? So essentially, when we get to our 4th step, how are we going to get to that point? Well, what we can do is we can take this and say, well, how do I go from 1 to 4? I multiply, right, by 4. How do I go from 4 to 16? I multiply by 4. Well, if I continue to multiply by the same thing, that's like our exponential function. So we're going to say that, let's say y, which is the number of trapezoids, is going to be equal to 4 to the power of n. And n is the step number. So if we want to go to step 4, we can say 4 to the power of 4, which equals 16. All right, simple enough. Not 16, I'm sorry, that was me multiplying 4 by 4. Not simple enough. 4 to the power of 4 is 4 times itself 4 times. So 4 times 4 times 4 times 4, which I believe is 256. Let me check that, and it is correct. Yes, 4 to the power of 4 is 256. Another way that you could do this is step 1 here is 4. We multiplied, then we multiplied by another 4. Then for step 3, we would multiply 16 by another 4. And then whatever that answer is, we would multiply again by another 4, which is the same thing as what I just stated. Now, if we want to find it when n is, say, 10, now we're going to put 10 up here as our exponent, and we're going to say 4 to the power of 10. So multiply 4 by itself 10 times, right? That's a really large number. You could find it out if you really were just dying to find out what that number is, but I mean, it's what, 1,048,576. But again, all we did was take n and put it to the exponent, all right? For number 2, it says at a certain step, we know that there are 262,144 smallest trapezoids. So those are how many we have. We want to write an equation to represent the relationship between n and the number of trapezoids in the step. So all we have to do is take that number that we have, 262,144, and we'll set it equal to 4 to the n. Now you might be wondering remember we had an a there before for our function, y equals a times b to the x, right? Because that's our exponential function. Well, in this case, a is 1, and the reason it's 1 is because at step 0, I was about to point to my screen, but that's not going to do you any good. At point 0, step 0, it's at 1, all right? So at step 0, it's a 1. That's our starting value, which is a. So that could be your relationship to that one. 1 times 4 to the n equals 262,144. Now, we want to explain to our partner how you might find that value of the step number. So what we're essentially trying to do is find the exponent you can raise 4 to get that 262,144. You don't have to be super explicit. So when I'm talking to my partner, or if I had a partner, or if I'm trying to explain to somebody else in the class, and they're like, well, how do you get that number? You're saying, well, what do we raise 4 to get 262,144? We could do a guess and check game until we get there, but there is another way to learn how to do that. And that's what our whole section is, right? From the beginning of your lesson here, where we're undoing operations, there is a way to undo n. You don't have to write that in for this blank, but there's a way to undo n, and it's called logarithms, and we'll learn it in a little bit. Let's look at 8.4. 8.4 is talking about missing values, okay? So again, missing values here, and we're going to create this table. Complete the value, complete the table here. What do we got? So we know that x is x, right? We're changing that value, and we know that the function is 2 to the power of x. So we're trying to plug in all the values that are here to get, right, that 1/4, to get that 1 over 32. Why don't we start over here on this side? Because this might be easier for us to find out what those x's are. Now, if I had 2 to the power of x, how do I get 4? Well, I raise 2 to the power of 2. 2 squared is 4. How do I get 16? 2 to the power of what gives me 16? Well, 2 times 2 is 4, times 2 is 8, times 2 is 16, so that's 4. So this x should be 4. It doesn't go in sequential order like we might think it does. 3 is between that, right? So what if we raise that to the power of 5? Well, we just did to the power of 4 is 16, so now multiply that by 2 again, and that's 32. For part 5, it's the same deal, right? Whenever we're looking at this, well, what do I multiply to get 256? Well, 32 times 2 is 64, so that would be 6. 6 times we've multiplied by 2. If I then did it again with 7 times, well, that would be 64 times 2, which is 128, so still not there. And then again, 8 times, so 2 to the power of 8 would be that 256. So that's an 8 right here. And then we need to continue that kind of trend, and you'll find it does grow pretty quick here. I believe this is just 10. But let's go back here for a second. Let's go back where I'm pointing at with my, I hope you can see my mouse. We'll see. Let's go back to the beginning, before -1. If you remember negative exponent rules, negative exponents tell us that we bring the fraction down. If I had a -2 here, that would be 2 to the power of -2. Negative exponents mean that that's going to now be 1 over 2 squared, which comes out to be 1 to the 4th. So if I look at this bottom fraction, it's a 32. I saw that 5 that was positive gave me a 32. So a -5 can give me that 1 over 32. Anything to the power of 0 is 1, back to exponent rules. 1/2, if I took 2 to the power of 1/2, that would tell me to square root it. So radical to rational there, a little rule as well. That's going to be the square root of 2. And then 2 to the power of 1 is 2. So there's my completed table. That's function 1. Look at function 2. Look, we can start here. That's like saying the square root of 5. This is like saying the cube root of 5. Again, radical to rational. So basically, whatever the denominator is in the fraction becomes the root. Whatever the numerator is in the fraction becomes the power underneath the root. So both of those powers are 1, but both of their roots are 3. Or well, this root is 3, this root is 2. But you don't put a 2 if it's a square root. Now, 5 to the power of 1 is 5. Now, where do I get 125? Well, 5 times 5, which would be a power of 2, right? That's going to give me 25. 25 times 5, which would be a power of 3, is going to give me 125. And then we try it again, right? If I take it to a power of 4, that actually does give me 625. Pretty quick jump there. And then if I take it to the power of 5, that gives me that 3,125. So 5 to the power of 5 is 3,125. Then if I go back, anything to the power of 0 is 1, back to exponent rules, if you remember those. I want to bring this down, -1, right? 5 to the power of -1 becomes 1/5. You see the 25, you know that's got to be a -2 here, right? Because 5 to the power of -2 is 1 over 5 squared, and 5 squared is 25. So that is your completed table with some added instructions. Go back and listen to me and instruct. I can't really write everything out here like I'd like to. I'm working on that. But go back through, look over that, see if you can get it right. Email me if you